You have learned the basic simplex algorithm to solve the optimization problem, but there are some types of constraints that we cannot handle with the ordinary simplex algorithm. That's why we're going to talk about a method which is still based on simplex algorithm, and we call it Big M method. Let's start. You may wonder why we need to learn Big M. Well, all the examples that we've solved so far, they all have the constraints in the form of less than or equal to. It means that when you convert these constraints into standard form, you add slack variables, and then you are ready with your initial BFS because you can use the slack variables as the basic variables. And then your table is already in a canonical form. However, that is not the case if you have constraints in the form of greater than or equal to and equality constraints. When you convert these constraints into standard form, they cannot form a BFS because the basic variable may be negative or you don't have a basic variable. So you will see later that in this cases where we have this type of constraints, we will need what is called artificial variables. So let's take a look at the example to see why we can't just use the ordinary simplex algorithm. In this example, Bevco manufactures an orange flavored soft drink. They call it orange, combining orange soda and orange juice. Okay, so you have a soft drink which is a combination of orange soda and orange juice. And then you produce the soda and you also produce the orange juice. So it's something that you need to produce, and then there is a production cost for producing the soda and producing the orange juice. And then when you read the word at least, you know that this is about the constraint. And then you also know that the size of the soft drink bottle is 10 ounce. It means that the amount of soda and juice that you put into the bottle of orange, the sum should be 10 ounce because the bottle size is 10 ounce. So whatever you put inside should sum up to 10 ounce. And then because the objective is to fulfill the requirement with minimum cost, so we have a minimization problem in which the costs they come from producing orange soda 2 cents here, and then 3 cents from producing orange juice. So you can say that in the definition of decision variables, x1 is the number of ounces of orange soda in a bottle of orange, and then x2 is the number of ounces of orange juice in a bottle of orange. And then we have a sugar constraint, we have a vitamin C constraint, and then we also have the constraint that a bottle of orange should be exactly 10 ounce. So whatever you put, the soda plus the juice, they must exactly equals 10. Again, because the size of the bottle is 10 ounce, so the content of the mixture that you put into the bottle must be 10 ounce as well. So we'll give you a pause to read this problem carefully and then also understand the formulation. Okay, so this is the formulation for the Bevco problem that we've seen before, and then we convert this into a standard form. For row 0, we simply move everything to the left-hand side, and then for row 1, because this is less than or equal to, we are adding a slack variable S1. Because the second row is greater than or equal to, we subtract it with excess 2. The third row is already equality, so we do nothing. And then so this is already in a standard form. All the signs are equality signs, and then you also need to write down that all variables non-negative. So this is the standard form. However, when you put this form into a table, you will see that we do not have a BFS, right? Because first you see that the table is not in a canonical form. Remember that for canonical form, you need to have 1 instead of -1 here, and then all the others in that column should be 0. So, and then for the last row, we do not have any variable which is which has the coefficient 1 and all 0 in the other rows. So this is 1, but again, this is not 0. So in other words, we do not have the basic variable for the row 2, and then we do not have basic variable for row 3 either. So the answer is no, because it is not a canonical form, and then we do not have basic variables for row 2 and row 3, such that this form is not an initial BFS. So now it should be clear why when we have all constraints in the form of less than or equal to, we have initial BFS readily available for us. But whenever we have other types of constraints, whenever we simply convert them into standard form, we do not have an initial BFS ready for us. So now I'm going to talk about the wrong idea. So sometimes people think that, okay, because this is -1 and then canonical form requires it to be 1, let's just multiply the entire row with -1. So this is how it looks like. So you multiply everything with -1, so it becomes -x1 minus 3x2 plus e2 equals -20. So now you have this table, but again, this is not a BFS. Why? Because the value of e2 becomes -20, but remember that we write this down that all variables, including e2, must be non-negative. So this is not the correct way. This is very wrong way to do that. So you cannot just convert into standard form and then multiply it with -1. This is a very wrong way. Do not do this. Again, this is wrong. Now this is the correct way to do that. After you convert the LP model into a standard form by adding slacks, excess variables, now you need something that is called artificial variable. Let me explain why this is called artificial first. So artificial means that it's something that we just make up. It doesn't exist. We just make this variable to help our calculation. So to compare this artificial variable with slack and excess variables, slack and excess variables, they actually exist in the problem. Because slack variable means the resources that we don't use, and then excess variable means that the amount that we overconsume something or the amount that we exceed the limits that we have. So they actually exist in the problem. But this artificial variable, they do not have any physical existence in the problem itself. So it's just something that we make up. So where do you need to put artificial variable? You need to put artificial variable whenever you have excess variable. So on the second constraint here, and also on the third constraint where the sign is equality, and then you see that you do not have any good candidate to become a basic variable. So that's why you put plus a2 in the second constraint and plus a3 in the third constraint. You do not add artificial variable for the first constraint because you already have slack variable, which is already okay to become a basic variable. Okay, and then do not forget to write down that all artificial variable must also be greater than or equal to 0. If we put this on a table, you will see that for the minimization problem, this table is already optimal because in row 0 you do not see any variable with positive coefficient. So this table is actually already optimal. But if you look at the solution closely, you ask, is this solution actually feasible in the original problem? So this is the original problem, and then we see that one of our basic variable here is a3 equals 10. Okay, so the last one here, a3 equals 10. It means that corresponding to this constraint, if this is the solution, it means that the bottle of orange that you produce contains 10 ounces of nothing. Why? Because A3 is artificial variable. It does not exist in the problem. It does not exist in the world. So it's just nothing, right? X1 is a non-basic variable, so X1 equals 0. X2 is also a non-basic variable, so X2 equals 0. So this is 0 and this is also 0. So the bottle of orange that you produce contains nothing. It means that this is a solution that is not feasible. Technically it's feasible, but it's not something that we want in the real world, right? You don't want to produce a bottle of soft drink, but then that bottle of soft drink contains nothing. So this is not correct. We want to prevent this from happening. We want to prevent this having an artificial variable in our optimal solution. So let's see how we can do that. The idea in the Big M method to prevent artificial variable occurring in the optimal solution is to give penalty for each of the artificial variable. Okay, so let's ignore the constraint. And then this is the original objective function. What Big M does is adding a penalty for each of the original problem. For the minimization problem, the penalty is plus Big M. So Big M is a very big, very large positive number. And then for minimization problem, the penalty is plus. It means that whenever you have artificial variable in your optimal solution, you will be given a penalty of very positive number. So using this new objective function, you will make artificial variable becomes very unattractive. That's why the simplex algorithm will try to not choosing the artificial variables to be included in the basic variable in the optimal solution. Okay, so let me repeat. In the minimization problem, you will penalize each of the artificial variable with plus Big M. Okay, so then we put this into row 0 by moving everything to the left hand side. So now you see it becomes minus m because we just simply move everything to the left hand side. And then you see this table now has a problem. It does not have basic variables for row 2 and row 3. What we want to do is this table, canonical form, and then each row has the basic variable. We can achieve this as usual using arrow, elementary row operation. So let's see how to do that. So this is the table from the previous slide. We do not have a canonical form, and then this is our what we want to have. So canonical form, because A2 looks like this, A3 looks like this, and S1 looks like this. So for each row, you have exactly one variable with the value 1 and all others are 0. So for this row, this is the 1 coefficient, and for this row, this is the 1 coefficient. So this is what we have, the table on the top, and then this is what we want. How can we achieve the table in the bottom? Well, you need to get rid of minus m here by doing this. The new row 0 equals the old row 0 plus m times row 2 plus m times row 3. So plus m times the entire row 2 plus m times the entire row 3. So here's the computation. You can write it down like that, or you just do arrow on the table. But if you do that, you will see that your new row 0 will look like this one here. Okay, so now you have a BFS, and now you see that this table is not optimal yet, because 4m minus 3 is a very big positive number. Remember, m is a very big positive number, so 4 times m is obviously 4 times a very super big number. So this table is not optimal yet, so let's try to find the optimal solution. Okay, as usual, you see for the minimization problem, there's still positive coefficients in row 0. It means it's not optimal yet. You pick the most positive coefficient. So 4m minus 3 is more positive than 2m minus 2. And then you do the ratio test, pick the smallest one, and then perform error and make that intersection between the entering variable and the leaving variable. I'm sorry, it's not very good line, but you see that here is the pivot. So what you want to achieve is this. The column x2 becomes 0, 0, 1, 0. So only 1 here in that position. What you need to do is first, the new row 2 here is 1/3 of the old row 2. And then once you have this new row 2, what you need to do is just perform error to make sure that the new row 0 in the column x2 looks like this. For example, to make this 0 means that the new row 0 here equals the old row 0 minus 4m minus 3 times the new row 2. Okay, so this is what you need to do for row 1 and row 3 such that you will get the table on the bottom. So this is the bottom table from the previous slide, and we see that this table is still not optimal because you see that you still have the most positive coefficient in row 0 is this 2m minus 3 over 3. So you perform ratio test again, pick the smallest one, and then the intersection between entering variable and the leaving variable here, it should be the pivot. Again, in other words, it means that your next BFS or next table should have 1 in that pivot position and 0 in all other position in that column. So perform error. The new row 3 here is 3 over 2 times the old row 3. Okay, so remember to perform 3 over 2 times the entire row 3. And then for the other row, this is what you need to do. The new row 0 equals the old row 0, 2m minus 3 over 3 minus 2m minus 3 over 3 times the new row 3. It may look complicated, but if you really understand error, this is actually just something that you need to do to make this value here 0. And this is what you need to do for the other rows. And then I strongly suggest you to pause this video and really try to do it by yourself on hand to make sure that all these arrow steps make sense to you. So this is the table or the BFS that we have on the bottom part from the previous slide. And we see now we do not have any positive coefficient anymore. It means that for minimization problem, this is already optimal. So now let's see if this optimal solution makes sense in the real world, right? Remember that before we penalize all the artificial variable, we have a bottle of orange that contains nothing. So here, this is the original problem, and this is the decision variable. So now it means that because x1 equals 5, so it means that we have 5 ounces of orange soda in our bottle of orange that we produce. Because x2 equals 5, because it means that we have 5 ounces of orange juice in the bottle of orange that we produce. And then the sugar content, because S1 is 1/4, it corresponds to the first constraint. So the sugar content that we have in a bottle of orange is 3.75, which is okay because it's still below the 4 grams that is the limitation in our constraint. And then the vitamin C is exactly 20 because we do not have any excess variable here. Now this is a feasible solution, and this optimal solution is also feasible in the real world because now the bottle of orange that you produce actually contains 5 ounces of soda plus 5 ounces of orange juice. So now it's good for us. The orange that we produce contains actually something that exists in the real world, which are soda and juice. So now you see that when we penalize the artificial variables, we successfully create a bottle of orange that contains something, juice and juice and soda. In the next video, I will summarize all the steps in Big M, so hopefully you will be able to see more clearly each step in the Big M. But for now, let me ask you a question to check your understanding. M is a very large positive number. So I have two questions here. The first one is, which one of these two is more positive? And the second question is, which one of these two is more negative? As usual, I will give you the pause on this video to give you the time to think, and I will give you the answer after the pause. So for the first pair, A is more positive than B, and then for the second pair, A is also more negative than B. Basically, you just need to pay attention to the coefficient of the Big M. You can just ignore any number that is after that. For example, minus 5M, minus 89974, 110, it doesn't matter. Minus 6M is more negative than minus M minus whatever. So you don't really need to care the other number. You just need to pay attention to the coefficient that is attached to the Big M. Okay, as I've said before, in the next video, I will summarize all the steps in the Big M so you can see the entire thing more clearly. So see you on the next one.